Well, shall we continue? Continuous random variables. This is section 6.1, part C. We're going to talk about continuous random variables. So the goal for today is to be able to find probabilities on continuous random variables. Yes, I have a spelling mistake. Hopefully you can find it. Hopefully I fix it later. All right, let's do a little recap. We got a couple things to review. I feel like a lot of this lesson is going to seem like familiar, and it should, because we've talked about a lot of this already. In Chapter 2, we learned about density curves and finding areas on uniform and normal curves. Density curves can model these continuous random variables. So continuous random variable can take on any variable or value in an interval on the number line. It's not just a set value like we've had before with the probabilities was a set amount. This can be like essentially an interval or a range. So if you recall, we learned about uniform. Now, underneath this uniform curve, the area is always equal to 1. But we could take any part of that and find the probability of falling in this range. Right? It's all based on the horizontal range. Now, we talked about normal curves, okay, where, again, the area still equals 1. But we would find, like, a chunk of it using what we learned about normal or approximately normal curves. And we've also learned about anything else. It doesn't matter what the shape is, whatever it is, it's still going to be 1, and we have to figure out for a certain range. So the probability of any event involving a continuous random variable is the area under the density curve and directly above the values on the horizontal axis that make up the event. So in other words, we're using things like the probability that x is less than 3. We're going with it's a range. And reminder, that's going to be the same as when we deal with normal curves, the probability that it is, let's say x is less than or equal to 3. There is no distinction. It is just the area from that line to the end in whatever direction. Okay? I'm going to make a note. There's an example. No single point we're looking for. Just kind of a range. Now, I'd like to look at an example of each, like a normal and a uniform one. So let's look at what we have here and try to answer a question based off of that. It says, your computer sends a request for the file to a web server, and the web server sends back a response. Let's say let y equal the amount of time in seconds after the start of an hour at which a randomly selected request is received by a particular web server. The probability distribution of y can be modeled by a uniform density curve on the interval from 0 to 3600 seconds. Draw the sketch. So if I'm taking that situation, I know it says the term uniform. So I know it's going to look something like this. And I know the entire area is going to be equal to 1 underneath it. But we're going to go from 0 to 3600. That's what's given. And I might label this as the amount of time the request is received, or for the request to be received. Okay, so based off of that situation, we can model it looking like that, and we can answer some things about it, like this question right here. Find the probability that the request is received by the server within the first 5 minutes or 300 seconds after the hour. Okay, so this is in seconds, so maybe I should note seconds. But we're looking for in the first minute, so 300 seconds. So let's just put 300 right here-ish. What's the chance that it's happening in that first 300 seconds? With uniform probabilities, we don't even have to look at the height of it at all. We're just looking, because it's the same height all the way across. We can just say, in this case, the probability, so this is the distribution of y, so we're going to say that y is less than or equal to 5 minutes, or you could also just say 300 seconds, would be that 300 out of the 3600 total that's on our density curve, which reduces to 112. Or if you want to put it into decimal form, it's 0.0833. And technically that's repeating, but that would be our 3 significant digits. So my answer would be there's an 8.33% chance that the request is received by the server within 5 minutes. Or maybe the first 5 minutes. But that's my context. So that's something that shouldn't be new to us. But that's kind of what we're going to be looking at today. We're kind of recapping, reviewing, going back to that and doing some things with these. Now let's look at a second example. It says the amount of Reese's Puffs that can be poured into a randomly selected bowl. I think we've actually talked about this situation earlier in the year, earlier in the curriculum. Is approximately normal with a mean of 44 grams and a standard deviation of 6 grams. The amount poured into a randomly selected large bowl is also approximately normal with a mean of 75 grams and a standard deviation of 10 grams. Assume the amounts poured are independent. You pour one small bowl, find the probability to get more than 50 grams. So we're just looking at the small bowl here. Okay? Now again, this should be familiar. It is approximately normal. That says it right here. So we're going to draw our normal curve. We're going to label the mean and the standard deviation, which for a small bowl was 44 grams and 6 grams. Okay. We're trying to find the probability to get more than, so it shouldn't have this word between in there. I'll get rid of that. More than 50 grams. So the 50 kind of falls, well, it's above 44, so we'll say 50 is about right there. And we want to find that probability under the curve here. All right? So how do you do that? We have to find the z-score. So that 50 minus the mean divided by the standard deviation should get us a z-score of 1. Since we want, and that does get you a probability. If you go onto your formula sheet, your z-table of 0.8413, which means the probability that's above that is 1 minus 0.8413, or 0.1587. So in other words, there is a 15.87% chance that one small bowl pour will be more than 50 grams. All right. So there's an example with a normal curve. Now, we've talked about what happens with these things called joint distributions. It has to do with transformations, how we are moving things, whether we're adding things together, subtracting things, combining things, looking at comparing. And I want to review that right now. If you think about multiplying, so let's just do a little recap. There's a difference between adding and multiplying. So adding or subtracting or multiplying. So we'll say adding a constant versus multiplying by a constant. Okay? When we add a constant, let's just take our random variable x and we add something to it. It adds something to everything, including the mean. So what that does is, same shape, just moves it, doesn't change the shape, but the mean will be increased by that much. The standard deviation, since it's the same shape, does not change. Okay, you're not actually adding to the standard deviation. It's not changing the spread at all. When you multiply, that's when it spreads it out. So if we take whatever our constant is, so we were just using that right there. So we'll say k for our constant here, times whatever our random variable is. That is going to keep the same general shape. Might make it more spread out, though. But if it's normal, it's still going to be normal. If it's uniform, it's still going to be uniform. The mean is multiplied by that k, so it is changed. Whereas the standard deviation does also change. So we'll say the standard deviation of x is multiplied by the k, but it's always going to be the absolute value of the k. Standard deviation can't be negative. So let's make sure it's staying as a positive. So just as a quick example, daily high temperatures for randomly selected November in Sussex, Wisconsin are normally distributed with a mean of 40 and a standard deviation of 6. What are the new mean and standard deviation if we change the temperatures to Celsius? Now, general shape is going to stay the same. It's still normal. The mean is not going to be 40 anymore. It's going to change. Now, if you don't know the formula for Celsius to get to Celsius from Fahrenheit, it is Fahrenheit minus 32. You can do some algebra to figure this out, times 5/9. So, this one's interesting. We are multiplying by 5/9, but for the mean, it is impacted by both adding or subtracting and multiplying. So I would take the 40, subtract the 32, multiply it by 5/9, and I get like 4.44 degrees Celsius. Oops, degrees Celsius. The standard deviation we just talked about is not impacted by the adding or subtracting. So we don't actually have to do that minus 32, even though it's in parentheses and seems like we should. We're just going to take that standard deviation and multiply it by 5/9 and get 3.33 degrees Celsius. It's only affected when you do multiplying. So a little recap there with that example. Okay. The same thing goes for like subtracting and dividing. If we go back to our example with Reese's Puffs, it says you want to change the units to ounces. So we're changing the units from grams to ounces. It's important to note that from grams to ounces, you would take the number of grams. So ounces is equal to grams divided by 28. Because it says there are 28 grams in 1 ounce. So we can write it like that. So it's like dividing the grams. We know the grams. It works the same as multiplication. Multiplication and division go hand in hand. So if I were to find, like, if we knew the mean was, what is this, a small bowl. So let's just do the small bowl. The mean was 44. That's in grams. We're going to change that, take 44 divided by 28, and that gets us 1.57 ounces. Definitely impacted. Everything impacts the mean. Standard deviation, however, you would take your 6 grams. That is impacted by multiplication, so it's also impacted by division, and we would get 0.21 ounces. So both in this case are impacted. So let's just do a little recap with a little table. We talked about adding or subtracting and how it affects the mean and the standard deviation. All right. So if we're taking two of the same distributions and for some reason we're adding them together because it's happening twice or something like that, the mean does get added. So mean of x plus mean of x, that's how we'd get the new mean. Standard deviation, assuming they're independent, I'm going to make that a big note. They have to be independent to be able to do this. The standard deviation would be the square root of the two standard deviations. So the x squared. So the variance is this what we're going to be adding up. Okay? That's going to always be our formula. So just as a reminder, that little guy right there, when you square the standard deviation, that is called the variance. Good recap there. Okay? Same thing goes if you're adding two different distributions. So x plus y. Say we're adding two different random variables. The means would be added. Okay? Standard deviation is the same formula. It's the square root of the variance of x plus the variance of y. Okay? Now, when we subtract, I'm going to make some room here. Our means do get subtracted. Same thing, nothing crazy there. But our standard deviation does not. It's always going to be addition under that square root. So it would just be the same thing. All right? And it's worth noting the shape, if it's normal, it's still going to be normal. Doesn't matter if you're adding or subtracting. So I do have one example of each of these things, let's say adding and subtracting, that I want to go through. We'll do an adding one, and we'll say this is all the same bowl. So same situation with these Reese's Puffs, but now we're going to pour out 3 small bowls. Find the probability that you'll be between 100 and 125 grams total. Okay? 3 small bowls. So you first need to identify what is your mean. Okay, the mean would be adding them. Because ultimately what we're doing is adding 3 small bowls. S plus S plus S. It is going to be a mean of 44 plus 44 plus 44. I don't know why I wrote standard deviation first. So you get a mean of 132 grams. So that's your average, what you'd expect for 3 bowls worth. Standard deviation, you're not just adding them together. Remember, if you're adding, you are doing the square root of the variances added up. So it ends up being 6 squared plus 6 squared plus 6 squared. I already put that in. I got the square root of 108. I'm going to leave it at that. Doesn't come out to be anything perfect. So if I want to find in between 100 and 125 grams, I know that's all to the left. So 100 is over here, we'll say. 125 is kind of close. We want to get that in-between area. We have to find the probability of each one to the left and subtract them then. So let's find those z-scores and use our z-table here. So the z-score for 125 minus 132 divided by the square root of 108. I got negative 0.67, which gives me on the table a probability of 0.2514 to the left. Now I want everything to the left of that, but I don't want to the left of 100, so I'm going to subtract everything to the left of 100. So I need to find the z-score for 100. Same way, just different value. I got negative, this is a 0.308. So there's not much to the left of that. I have written down a probability of 0.0010. So if I subtract those, I get the in-between, which is 0.2504, which means there is a 25.04% chance that 3 bowls will end up between 100 grams and 125 grams. All right? So I would maybe summarize that on an FRQ by saying 25.04% chance of that happening. Okay? So that's what an addition one looks like. You can do the same thing if you want to take that situation and deal with a large and a small bowl, but you're still going to do the same sort of deal with adding. Okay? I want to jump to one last one that deals with subtraction. So same deal here. Question is a little bit different though. It states You pour one small bowl and one large bowl. Find the probability the small bowl contains more than the large bowl. Now, think about the situation. It probably shouldn't happen. It's going to be low probability. But it could, and there's always a chance. So we're going to find that chance. All right? This, again, is something similar to what we've done in the past. We want to know, in this case, what is the chance that a small bowl is greater than a large bowl? In other words, we could also write it as a large bowl pours out less than a small bowl. Now, you can choose which way you want to go. We do probabilities based on less than, so maybe you want to choose the less than one. I think that's the one that I'm going to use right now, is the less than one. Okay? So, to build this out, we need a number, because in our normal curves, we need a number to go off of to find the z-score. All right? And right now we don't. We just have, I'm going to use that second one. L is less than S. So to get a number, I'm going to subtract a small bowl from both. So I have L minus S is less than 0. Then I have a number that I'm dealing with. Okay? Now, L minus S, we are subtracting. So the mean would be a large minus a small. So that's 75 minus 44. And you get 31. That is your number. Okay? The standard deviation will be the square root of 6 squared. So that's each of it. Doesn't matter that we're subtracting now. It is still adding the variances in here. 6 squared plus 10 squared, which actually gets you square root of 136. Not a perfect number, but that's what we're going to deal with. And then the number we're going to look for is, it's saying that the large minus small, which we're modeling here, is less than 0. So 0's got to be somewhere over here. All right, and we want to go less than 0. So since it's a less than, it's going to make our life a little bit easier, because that's how the probability, the z-score table, the z-table works. All right, so my z-score for this would be 0 minus 31 over the square root of 136. I calculated that you should get a negative 2.66. Okay, go to your z-table, and that will give you 0.0039 to the left of it. So my drawing is not perfectly accurate, because I knew it was going to be a small probability. This is really low. But I could then conclude that based on my information, there's a 0.39% chance of a small bowl being filled higher than a large bowl. And I would want to put more words there, but this is what I'm going to summarize here. Okay? A lot of this is similar to what we've done in the past. Okay? It's not a whole lot new, but we are working with those transformations on different continuous random variable distributions. So that is section 6.1c. We'll see you next time.